Hi, good evening, everyone. Let's wait for like 5 minutes more so that we'll allow others to join in before we get started. All right, thank you. Yeah, so while we wait for others to join, we have here with us Mr. Dashun, right? So hi, Mr. Dashun. Can you hear me? Okay. Can someone hear me?
We can hear you.
Okay, I believe Mr. Dashun may not be available at the moment here. All right. So we have 3 minutes more to get started. Hi, good evening, everyone. Once again, it's 8:35. Yeah, so I'm pleased, to welcome you all to the first episode of NAIJA-JUG's data structures and algorithm session. Yeah, and today we'll be exploring big O analysis. Yeah, and we have with us Mr. Jonathan to handle the session. So just for for a little context, right? Mr. Jonathan is an experienced software engineer, and he has a lot of good nuggets to hand to each of us this night. So please pay attention and lend him your time. But before I call on Mr. Jonathan to take the floor, so I want to, to also welcome Mr. Dashun. Mr. Dashun is among us. Can you hear me, Mr. Dashun?
I can. Thank you for everything. Yeah, we're here. We're having fun. I'm excited. I'm excited to see today's session. And then just my reminder, like every rep counts. All of these little extra sessions, just pay attention and then go practice it. Put it to work.
All right, great. Thank you, Mr. Dashun. All right. So, Mr. Jonathan, please have the floor now. Thank you.
Yeah, thank you, Bright. Yeah, thank you for the introduction. So, good evening, everyone, once again. So, today we'll be looking at big O analysis, which is an integral part of data structure and algorithm. In most data structure and algorithm questions and interview sessions, there are questions that interviewers usually ask. So it's not just about solving an algorithm question, but you also need to know the running time and the memory as the input size grows. So I'll be sharing my screen to take us through this. Hello, can you see my screen? Okay. So yeah, so our topic for today is big O analysis, and then the two aspects of big O analysis. So when we talk about big O analysis, we are talking about the study of how an algorithm, the time it takes an algorithm to run as the data scales or the input size increases, the worst case, and then the memory consideration, how much memory is used as the data increases. So just like I said, what we'll be looking into is how fast a piece of code run and the amount of memory which this code used to run. So we'll be taking some example, but before we go there, I would like to give a background, a computer science intro to this. So before we go into the algorithm part. So there are common time complexities and memory complexities when dealing with, when we talk about big O notation or big O notation. Yeah. So one of it is the constant time. So just like when students write exam, there are ways you grade exam score. We have A, which is The highest score you can get. Okay. I can see this, yes. Can you still see my screen? Hello?
Yeah, we can.
Okay,
Yes, I can see your screen.
Okay. So just as I was saying, so when students write the exam, there are conventions that is used to grade exam score. We have A, we have B, we have C, then D and E, and there are scores that determine what an A grade is. Same with B. So using similar example, there's a convention we use to grade the performance of an algorithm based on the time it takes to run, which is the time complexity. So we have a constant time. So the constant time talks about no matter how the input size changes, there is a fixed operation. And a fixed operation is being carried out. So that is O of 1, constant time notation. Then there is O log n. For O log n is a logarithmic approach. So when we talk of logarithm in mathematics, when you take the log of a number, it does not grow exponentially, or the change is not too much as compared to a quadratic growth or an exponential growth. So let's take, for instance, let's compare the changes between the log of 4 and the log of maybe 16. Yeah. So if you compare the difference between log of 4 should give us 2, I think. I don't know if you are getting me. Hello?
We're following you, sir.
Okay.
Sorry, please. Are we expressing the log in base 2?
Yeah.
Okay, sir.
It's in base 2. Yeah, but in algorithm, the base does not matter, but we'll be expressing in base 2. So I just want to give example why. I just want to explain. So when you come across log n, time complexity, or n log n, you should understand what it means. So what it means is that the growth is minimal compared to O notation n, which is the linear time. So if you take the log of 4, it will give you 2. And if you take the log of 8 or 16, log of 16 should give us 2 raised to power. Should give us 4. So there's no much changes there. There's no much changes for logarithmic time. So for linear time, it talks about the running time scales linearly. So if, let's say we have an array of 9 inputs. So the worst, if we are asked to look for an element in an array with 9 inputs, let's say we have 1, we have 2, 3, let's say 6. Okay, 1, 2, 3, 4, 5, 6. Okay, we have an array of 6 elements, and we're asked to find the biggest number in this array. What we mean by linear time is it will take us 1, 2, 3, 4, 5, 6, 7 iteration 1, 2, 3, 4, 5, 6. It will take us 6 iterations to get to the biggest number. Let's assume we increase the size of the element in this array to 1 million. The way we increase the input, if this is norm, we wrote an algorithm that accepts a number, an array of norm, which is of size 6 for this example. If the worst case to get an element in this array is to get the element at this point, which is the last element, and it is at the, it will iterate for 6 times to get the last element here. So let's say we have an array that contains 1 million elements. So it is going to take us also 1 million iteration to get to an element at the last index. If we start from 0, so that would be 999,999 or thereabout. Yeah. So for this O n log n, it is a combination of the linear time and the logarithmic time. We'll still show an example that deal with this. A good example of this notation is when you want to insert an element in a heap. I don't know if we've done anything on heap, but during our subsequent classes on Saturdays for the data structure, when we start solving examples, you will see some of this implementation when we get to binary tree. So when you insert an element in an ordered binary tree, which is a heap, for an example, you don't go through the whole node since it is ordered. Sorry. You don't go through the whole node. So you go through, depending on which side of the node has the bigger size of the element, you go there. So it follows a kind of binary search implementation, which is a good example of this O log n. So whenever you see O log n, a good example is binary search. So for each iteration, you divide the input size by a constant factor. Whenever I see such a situation in your algorithm, it is of this example, O log n. Then when the input size, when the running time is linear compared to the increment of the input size, it is a linear time, which is this. So when you combine this and this, you have O n log n, which is linear-arithmetic time. It's called linear-arithmetic time. So when you're for O n square, most examples, so the naive way of saying it is when you have a nested loop. For example, you want to do a comparison between numbers in an array, and you want to do it using a nested loop. So you have a loop that goes through this element, this array, and each time it goes through this array, it compares each of the elements with every other subsequent element inside this array. When you are in 2, you compare 2 with 1, 2, 3, 6. So in such a way, it's going to be n multiplied by n. We're also going to see an example of this. So another one is another example is the exponential example, which the exponential time, another big O notation for time complexity is the exponential time. This particular situation are rare, so you mostly come across it when you are doing recursion or recursion. And a good example is the Fibonacci series. If you want to compute the factorial of a number, a good example is following the Fibonacci approach. So in such a way, you encounter this, but it's a rare occurrence. You hardly come across this in your interview questions. So we also, apart from time complexity, which is computing the time it takes an algorithm to run, another thing we consider in O notation is the space required to run the algorithm. So you want to see if the memory allocation changes depending on the input size, or it remains the same, or at what rate does it change. So these are some of the questions that are mostly asked in interview sessions. So for space complexity, we have the constant space, linear space, and quadratic space. I can't see the meeting chat. So in case anyone has a question, you can ask the question. So the moderator will tell me to pause. So you can ask your question. Should I go ahead?
So far, I don't think there's any question. You can write down.
Okay, thank you. So in doing the analysis, in computing the running time of an algorithm, there are some things I want us to have in the back of our mind. So the way we want to go about it is to compute the running time of each line of an algorithm. So one of the things we want to have in mind is for mathematical, relational, assignment, and return statement, we count it as one operation. In reality, there might be multiple operations, but from the perspective of computing big O, they are constant. Thus, we ignore the details. Okay, so let's look at some example. So let's take this algorithm for example. Like the previous slide said, mathematical expression, comparison, and assignment, we denote it as one operation. So the next slide will be able to do justice to this. So looking at this, we want to compute. Let's assume you went for an interview and you are given an algorithm to do something like this, a simple operation to compute, given a number, you want to increment from 1 to that number. You want to sum from 1 to that number. Let's say we are given 5 here. We want to do 0 plus 1 plus 2 plus 3 plus 4 plus 5. And you want to, so after solving such algorithm, you are asked to give the running time of the algorithm, which is the worst case scenario. And you want to do it line by line. So for example, in this case, this is an assignment. We are doing declaration and assignment here. So it is seen as one operation. In this line 2, this first statement, we have a declaration and initialization here, which is seen as 1. So better still, we can use this part. So we have, for this line, for this first statement, we have one assignment, one comparison, and one increment done n times. This is it here. So for this line, we have sum is equals to sum plus I. So it is one addition, one assignment done n times. The n times we are talking about is this. So if we have 5 here, this operation will happen less than or equals to 5 times. So this is determination criteria for this for loop. So we want to deduce the running time of this algorithm step by step, following a step-by-step operation. So this particular line is, we are doing one addition, one assignment, done n time, because this iteration is going to run n time or norm time. So this is If you open this bracket, n multiplied by 1 plus n multiplied by 1, this will give us n plus n, which is 2n. A return statement, like the previous slide said, is denoted as one operation. So we have 1 here. So if we sum everything here, we have 2n plus 2n plus 1 plus 1. This is 2 plus 4n. Okay, we have this one, 1, 1, 1, which is 3. Then we have 2n plus 2n, which is 4n plus 3. But in big O, we don't consider constant values. We only consider the rate of growth. So in this case, 4 here does not count and 3 here does not count. The only thing that counts here is this n. So we say this is O of n. So, and like I explained earlier, O of n says that this algorithm, depending on the input size, even if the input size increased to 1 million, the rate of change is going to be linear. It's not a constant, it's not going to be constant, and it is not going to be O of n squared. So this is the way to deduce the running time of an algorithm. We'll look at another example. So this is the time complexity of this algorithm, which is O of n, like we deduced in the previous slide. So the space complexity is O of 1, because the variables are not going to, the memory usage are not going to change, no matter the input size, because we've already catered for the variable definitions. So there's a memory location already from the start of the algorithm for some I, and so we only used 2 variables, sum and I, there. We'll look at another example, which is example 2. So looking at this algorithm, there's just one line of code here. So what we want to do is, given a number, we want to multiply the number by, we want to add 1 to the number, multiply it by itself, and divide it by 2. So like the previous, our working principle, addition, mathematical operation, initialization, or comparison or assignment is referred to as one operation. So in this case, we have 1 addition, 1 multiplication, 1 division, and 1 return statement. So all of them are constants. 1 plus 1 plus 1 is 4. And 4 in this case, there is no changes here. No matter the size of, no matter what this norm is, this is going to happen. This is a constant operation. It's going to happen once. Even if this norm changed from 5 to 1 million, it's going to be a constant operation. So that is why the time complexity is of 1. And the space complexity is of 1. Also, there's a principle that says that the space complexity of an algorithm, in most cases, will either be equals to the time complexity of the algorithm or less than the time complexity of the algorithm. So if you write an optimal code, in most cases, the memory it requires to run will not be worse than the time complexity of the algorithm. So in most times, consideration are mostly paid on the time complexity as compared to the memory usage. We'll look at the third example. If you have question, you can ask before we continue.
Yeah. Hello, can you hear me?
Yes, I can hear you. I can hear you, Bright.
I have a quick question, please. So, like, at what point, do you focus on optimizing for space? Like, what should trigger that decision to either focus on optimizing for space or optimizing for the normal time complexity? Do you get me?
Yes, I get your question. So some factors that warrant optimization is, first of all, you should be able to know the time complexity of that algorithm and the space complexity. So to know if you can further optimize it. So if you look at a situation whereby you have a time complexity of O of n square, you can further optimize it to maybe O of n log n, or O of n, or even constant time. So in this session, our focus is not on optimization of an algorithm. It is to be able to compute, like after solving an algorithm, you should be able to tell that, okay, this is the running time of this algorithm, and this is the space complexity of this algorithm. In such a case, you'll be able to know that you can further optimize this, or this is the best solution you can get.
Okay, thank you very much. Thanks.
Yeah. So this particular example is a bit tricky, unlike the other ones we've seen before. So we have two for loops here. They are not nested. And this algorithm have two different inputs. Oh, fuck. I've made a mistake. I think I need to stop sharing and go back to another slide. Because this platform I'm using, I will not be able to go back. Can you still see my screen?
Yeah, we can see it.
Yes, it's good.
Okay, yeah, I think I'm going to use this instead of the other one where I can't go back. Okay, so looking at this algorithm, we have two different for statements dealing with two different input type, N and M.
Sorry, Mr. Jonathan. I think Mr. Davis' hand is up.
Okay.
Yeah, I'm sorry. What I wanted to ask is, can you make this full screen? I think there's a way you can make this full screen so that we
Can
can
you hear
see
me?
what is. Yeah, like maybe put it in presentation mode so that we can really see especially the breakdown. Also, I don't. That should be possible.
Yes, presentation mode here.
Yeah, thank you. Thank you very much. Thank you very much.
Okay, so yeah, looking at this example, we have two for statements with two different input size. Let's say this algorithm is accepting M and N. So if you look at like the approach we are using right from the start of this session. So this is an assignment here, two assignments, 1, give us 2. So this operation is running an n time. We have an assignment here, one assignment, one increment, and one conditional statement done n times. That gave us this. So we have 2n for this operation, just this block of code. Then for this one, we are using m and we are not using n here. We are using m instead of n. So there are two different input size. The only time n and m is the same is if the input size is the same. if m is equals to n, the size of m and n are the same. So after deducing this, it gives us O of n plus m. This is not part of the time complexity I shared earlier. If you can remember, there's nothing like n plus m there, but mathematically, you can deduce. There are so many time complexity you can deduce, and depending on the size of m and n, you'll be able to determine if the running time of this algorithm is faster than ordinary O of n, or it is a worst implementation compared to O of n. But we can still see it is not a quadratic or a polynomial time complexity. So it still falls under the category of constant linear time, not constant time, linear time, sorry. So the time complexity for that example is O of n plus m. Then the space complexity is constant, because no matter the input size m and n, the amount of memory required for this implementation will not change. We are not copying anything. We are not copying anything, or what are factors that can affect the memory size of an algorithm. Yeah, we are not doing any copy. So that is one situation whereby, for example, in Java, your array is static. If you define an array of size 4, and you want to add 4 elements to it, the amount of memory you need is constant. But at a point in time, you have 5 elements or more, which is bigger than the size of the array you declared initially. Then you are going to do a copy, then increase the size of the array. So the memory is no longer equals to the original memory at the start of the application. So in that case, the memory requirement or the space complexity is not constant. It changes as the input time change. But in this particular example, no matter the input time n and m, the amount of memory required to run this algorithm will still be constant. That is what this means. Okay.
Yeah, so Mr. Davis' hand is up.
Okay.
Okay, sorry for disturbing. Well, I'm sorry for disturbing your session, but I wanted to ask a question concerning what you just said about the space complexity. What if, for instance, the algorithm makes use of an array list that keeps changing its size? For instance, like maybe during the mid operation, it keeps, maybe there's just a very weird algorithm that makes use of an array list that just keeps maybe changing its size or modifying its contents and stuff like that. Is that another factor that could affect the space complexity?
Yes, in case of array lists, there's something called amortized time space complexity. So the underlying implementation of an array list caters for capacity. There's something called capacity in the underlying implementation of an array list. So at every insertion, it doubles the previous size of the array list. So if the initial implementation declared a size of 10, and you keep inserting into the array list, and at a point it gets full, so the capacity will be doubled to 20. So if you notice, if you add from when you added the last element that made the size to get full, you still have like a constant time. Each additional element you add will have a space complexity of O of 1. I don't know if you get what I mean.
I think I understand. Thank you. Thank you very much.
Okay, so you can, to properly get, you can look up amortized space complexity for an array list. You get what they did there. So looking at this example
Thank
4.
you.
Yeah, you're welcome. Looking at this example 4, following our approach, so we have a nested for loop here. And our input size is n. So for each iteration we do for this external for loop, we are going to iterate for number of n. Let's say n is 5. Let's say n is 5. And we start from the first iteration. So this will run 5 times and come out again. Let's say we are checking for, we have an array of numbers, and we want to compare, we want to get the biggest element in that array. So if you move from the first value at the index, that is the most cases where this type of implementation is done. You check, you use the first element in that array to compare every other element in the array. So in that case, you have an n times n operation, which will give you n squared. But narrowing this down line by line, this line is, we have 2 assignments here. In this line, we have 1 assignment, 1 increment, 1 comparison, and one comparison done n times. Then in the inner loop, we have 1 assignment statement done n times, 1 increment, and comparison done n times n times. Then this is 1 assignment, 1 addition, and 1 assignment. Yeah, done n times n times. So if you compute this and look at everything, we have 4n squared plus 7n plus 4. The worst case here is n squared. So we will not consider this 7n and this 4. And just like I said before, constant values are not considered. So instead of saying the time complexity of this algorithm is 4n squared, you just say n squared, because at in the large scale, this 4 does not affect, does not matter. Looking at the big picture, the 4 does not matter. What matters is the rate at which this grow, which is a quadratic rate. Yeah, question?
Can you hear me? Hello? Hello?
Yes, I can hear you.
Yeah, so I have a little bit of a question on the quadratic time. Yes, I can see that, if we have like 2 nested loops, that is a loop inside a loop, there's a tendency of having the quadratic time, right? Yeah, from the example you showed, you can see that the nested loop, kind of runs the entire length of the array, that is the n, right, for each element of the outer loop. Now, the question is, what if you have an inner loop whereby it doesn't run for the complete length of the array? For example, it runs maybe half of the array, or it runs, the length of a different array, which, the outer array is not really, iterating over. What complexity can we have on that? Is it still the same quadratic time?
Okay, let's assume this inner loop is m. They are not of the same size with this outer loop, which is the question you asked. So in such a case, since they are not the same, it's not going to be quadratic time. It's going to be this multiplied by this. So in such a case, it's going to be O of n multiplied by m, which is O of nm or mn. And the only case where it is going to still be in the same case with this is when the two elements, m and n, or any other value, a and b, are the same. But if they are not, if the length is not the same, it is going to be how many times this run multiplied by this. So if they are different size, let's say another value entirely or another input size, maybe in a case where we are doing something with we are dealing with what is it called, row and column, a grid or thereabout. We have
Okay, thank you. Thanks.
yeah, so in such a case, it is not going to be O of n square. It is only O of n square here, because for each time this outer loop runs, this one is going to run the same number of times.
Because Lukun's hand.
Hello?
Yes,
Sorry
yes,
to cut
my. Hello.
Yeah, hello.
Yeah, go ahead, Balogun, please.
Yeah, so just a quick question, right? So while you were kind of evaluating the n stuff, right, there is an n that was like you have 4n squared plus 7n. So you said the n is to be ignored. So like I just want to, can you please just shed more light on that? Because the n is a very big factor. Like if you are considering it mathematically, like the n can play a big role. So like why do we have to ignore it? Since we can have like a custom notation. So why can't it be n squared plus n? I just need more clarification on that. Thank you.
Okay, all right, thank you. So big O in its entirety is dealing with worst case. Worst case, so n square is worse than n. So you consider n square. I don't know if that answers your question.
Yes, thank you.
Yeah.
N square, yeah, n, yeah, thank you.
Yeah. Okay, so go to the so the space and time complexity of the past example is the time complexity is O of n square and the space complexity is constant space. So the example, the explanation I gave earlier about O log n. So if you look at this example, each time we run this while loop, we divide the input size by a constant factor, which is 2. So we are not going to loop, iterate through this, the total number of n, let's say 5. We are not going to do while I is greater than this block of code seems not to be correct. I lifted this from somewhere, so yeah. So we are not going to run this the entire length of n. So a good example of O log n time complexity is when you are dividing, for each iteration, you are dividing the input size by a constant factor. Just like in binary search, if you want to look for an element in a sorted array, you first of all divide by half, then you check if it's at the right or the left-hand side, depending on the size of the element. Then you divide again, you continue. So that is why this the time complexity of this particular algorithm is O log n. Some people will look at this algorithm and say it's O of n because there is a loop here. That is the mistake some people do. When they see a single for loop, they assume the running time of that algorithm is O of n. Or when they see a nested for loop, like the example Bright gave, they assume it's O of n squared. So you need to pay attention to some of the underlying implementation. Sometimes it will look like O of n squared, but the implementation is either O of nm or something more efficient than what you think it is. So that is why we do analysis line by line to see from top to bottom to calculate the running time of the algorithm and the space complexity as well. Yeah, a question?
Yes. So I have a question based on this, log time. So what if, you have a loop whereby for each iteration, you are, let us say, increasing the iterator by 2, right? It's not like you are dividing now, but, for each iteration, you times the iterator by 2. So is this still this, logarithm time?
No, it's no longer
Even
logarithm.
though you are just using the normal for loop, but for each iterator, your increment is timesing by 2. So is it like still the same log, or is it a different time complexity?
It's not going to be O log n, if I get it correctly. Why it is O log n? Remember, O log n is more efficient than O of n. I want to make that clear. O log n is more efficient than O of n in the sense that you are not going through the whole item. So if you have, if this is 5, we are not going to loop 5 times here because we are dividing this input size by 2 each time we iterate over this. So it is going to give us a more efficient running time compared to O of n, which is running over the whole input size. I don't know if you get what I mean, Bright.
Yeah, it's clear. I'm just confused on, that when you say for I equals to 0, where I is less than n, then you now say the I plus plus. Now in that I plus plus, what if we switch that I plus plus to I times 2? Meaning that you don't even need to go through the entire array. You are like jumping, for example, by
Is
2
it
each
on
time or
this?
something like
Is
that.
it on this screen I'm sharing now?
It's not exactly right. I'm just looking at, okay, since this algorithm kind of divides, right? If we also use a for loop times by 2, is it still same logarithm time?
I'm not able to picture the question on my head. If I can do that, I'll be able to deduce the running time of what you're saying.
No problem. I will send that to you later. Yeah, thanks. Yeah.
Okay, thank you.
All right, thanks.
Yeah, question.
Yes, good evening.
Go ahead.
So for this example 5 now, at what point do we know that is a logarithm of n? Because I think on the first line of the while I is greater than 1, we're able to see that log n is there. So at what point do we know that this is a logarithm of n before we even start looking into the code of the while loop.
Okay, looking at you know while loop is a type of for loop.
Yes.
So this is the condition that this is the is it the iterator and the increment and decrement? What determines how many times this will run?
Okay. All right. I think I get it now. Thank you.
Yeah. So the device I'm using, I wish I switch from the annotator what is it called, plugin I was using. I wish I'm able to write, so I'll be able to maybe mathematically prove to you. So when you see an algorithm, you'll be able to know that it is O log n. If you are not going through the entire element, you can consider it as O log n, but it is not entirely true. Because in some nested for loop, you don't need to go through maybe the outer loop, you are going through everything, but the inner loop, you are maybe skipping, you decided to start from 1 instead of 0, or the first index. So, but just take it that when you have a common, when you constantly divide, just like in divide and conquer algorithm or binary search implementation, where at each iteration you divide the size of the element into 2 or a constant factor. In that case, it's O log n.
Yeah. All right. Thank you very much.
Yeah, you're welcome.
Okay. Please, there is also a question on the chat box. So I'm going to read it out to you. Then you answer the person.
Okay.
Can you hear me?
Yeah, I can hear you. Go
Yeah,
ahead.
it says, am I always giving the solution to find the O notation, or a problem to solve and find the notation?
Oh, in most, it depends on
Do you
what.
get that?
Yeah, I think I get the question. So it depends on the nature of the interview. But if you interview with some big companies, obviously you have to solve the question, and sometimes it's live, like a live session. You are solving the question and there's someone there. At each line, they want to know if you even know the time complexity of every line of code you write and why you made that decision. While in some cases, it might be an online platform. I've done an interview with one company, and one of the questions they asked was different type of, it was more like an objective. So they give an algorithm and you pick what you think is the running time of the algorithm. They give you options. So you pick from it. So it depends on what the interviewers want. But in most cases, what they do is after solving an algorithm, the interviewer will ask you what is the running time and time complexity. They might decide to ask you the time complexity of maybe from line so to so, or a block of code, or the whole algorithm. So yeah, it depends. It is not fixed. So you just need to know how to deduce it.
Okay, thank you.
Yeah, you're welcome. So yeah, the time complexity of the example 5 is O log n, and the space complexity is constant space. So like I said earlier, the rules of big O is constants are ignored. So if you look at, if we start deducing from here, we have, after our analysis, if you have something like this, obviously, you know, the worst case here is n squared. So, but first of all, you eliminate the constant, which is 5 here, 6, the coefficient of n squared, 5 here, 6 here, then 4 is, you change 4 to 1, then you drop the lower order terms. So n square, the growing rate of, if n is 9, of course, the rate at which n square grow is higher than the rate at which just n grows. So the lower orders here are n and plus 1. So you have your n square left. So variables are combined only if they refer to the same input. If you have an input, if at the end of your analysis, you end up with, let's say, O of m plus n, you cannot add m plus n. So your final solution is O of m plus n. So you always assume the worst case analysis. So in this case, the worst case here is n squared. Yeah, so that is the rule of big O. So yeah, this is something we have to also consider. So improvement has more to do with being brilliant and basics than a focus on complication. Yeah, this is a quote from Lombardi. So yeah, and most of what I used here was lifted from this article, Introduction to Big O Notation, Time and Space Complexity. You can look it up. Is a post on Medium by Chinenyo Keke. Yeah, thank you.
All right. Great. Thank you, Mr. Jonathan, for such a powerful session on Big O analysis. Yeah, so I believe we've all learned a lot. So we'll officially open the channels for question now. So if you have any question, do raise your hand up, then you be called and you ask your question. All right, thanks. Okay. I think there's no question, though I still have a question to ask. Yeah. So, sir, my question is on, we have this, space complexity and also, time complexity, right? So when solving, for example, a lead code question,
Yeah.
for example, you are giving, an interview question, right? What should be your focus? Should you focus on optimizing for space, or should you focus on, optimizing for time? Because I saw that some of the algorithms you give, some are constant, time for space, constant space, while some are, linear time complexity. So what should be one's focus when solving interview questions?
Okay, thank you very much for that question. So when solving interview question, is more important to focus on time complexity, because in most cases, like 90, it's rare to come across an implementation where where the space complexity is worse than the time complexity of a particular algorithm. What do I mean? If you solve an algorithm and you get, let's say, a time complexity of O of n squared, the space complexity cannot be worse than O of n squared. In most cases, it will even be less. Maybe a time complexity of O of n squared or O of 1 or O of n. So an optimized solution in time will in most cases be optimized for memory.
Okay, thank you very much. That was okay. Yes. Yeah, thank you.
You're welcome.
Is there any other question? All right. So I have dropped, the link to our channels on the chat. It contains, the link to our LinkedIn, the WhatsApp group, and also the S channel. Right. So we would love to have you join our community, and we have our lightning talks on that is on Tuesdays here. Then also we have the monthly sessions where we bring in, notable figures in the industry to come speak to us, to come expose us to what is happening in the session also. So we'd like you to join the channel so that you'll be up to date with what is happening. Yeah, so once again, since there is no question, thank you everyone for joining today's session. And also thank you, Mr. Jonathan, especially for doing justice to this topic. Personally, I learned a whole lot, a lot of clarifications here. Yeah, so I don't know, Mr. Sam, do you have anything you would like to add before we draw the curtain? Mr. Samuel, are you there? Do you have anything you would like to say?
So can you hear me?
Yeah.
Hello.
Yeah. That's clear.
Okay.
Yes, clear. Go ahead.
Yeah. Nothing. I don't have anything to add. Thank you very much, Mr. Jonathan, for this wonderful presentation. Also, okay. I just want those of us that have gotten our boot camp is starting by upper next week. So for those of us that got in, congratulations, and would love to see you grow. You get, and so and those of us that are already in the community, we have lots more sessions to come, and to keep your eyes open for there are lots of what they call it again, hackathons for Node and other stuff. We've never had one for Java, so we plan on doing that also. So just keep your eyes up. We have lots of things coming up, and just stay glued. Thank you all for joining in. Thank you very much. Have a lovely night. Mr. Bright.
All right. Thank you, Mr. Sam. Yeah, so here we'll draw the curtain today. Until next time, I'll see you guys. Take care. Bye-bye. And do enjoy your sleep. Bye.